Good day and welcome back to part 2 of our discussion on limit laws. In the previous video we went over the first 5 limit laws and paused for an example. In this video we're going to pick up where we left off with the remaining 5 limit laws. So to begin, the limit as x approaches a of a function raised to the nth power. Remember, the limit laws, as I mentioned previously, are kind of telling us we can do exactly what we want to in terms of what makes the most sense. We can go ahead in this case and substitute or push that limit inside the nth power of a function. The 7th limit law, and you don't have to know the numbers, this is just to kind of correspond to what you'll see in the textbook. The limit as x approaches a of c. So we're thinking c is representing the function we are taking the limit of. That is, if we were to maybe graph it and think about it from a graphical perspective, we would have a graph of the curve f of x equals c, or we might think if c is positive, y equals c. So as x approaches some a value, that's asking for an input close to a, well, what are those outputs going to be close to? And it's not necessarily what those outputs are going to be close to, they are exactly equal to c. That is to say, the limit of a constant is always at constant value c. Similarly, in the 8th limit law, the limit as x approaches a of the function x, we can think about this very intuitively again from a graphical perspective. The function we are dealing with is y equals x, so a line going through the origin with slope 1. And we want to know what is the limit as x approaches any constant value a. And it could be positive, negative, even 0. I'm just picking a positive value to draw this nice and easily. Well, we know that because it's y equals x, we have this point AA on our curve. And if we have an input close to a, if we trace that over, we see that the output is also close to a. So in this case, the limit as x approaches a of x is always going to be equal to a. And note, if I say this in words, it almost sounds a bit silly. For x close to a, x is close to a. The idea of a limit. Now for the 9th limit law, we could actually combine together limit laws 6 and 8 to explain why this is true. So in terms of x to the nth power, we can really think of x as playing the role of the function in limit law 6. And that 6th limit law tells us we can take that limit as x approaches a, and we can substitute it in, or push it through that nth power. And then what remains is precisely what we saw above in limit law 8. So we end up getting a to the n. And just to write this so that we can all see it very clearly, this limit law is that the limit as x approaches a of x to the nth power is a to the n. So for x close to a, x to the n is close to a to the n. And then lastly, our 10th limit law, once again, kind of tells us we can do what makes intuitive sense. A limit can be pushed inside an nth root, and specifically say a square root. So this becomes the nth root of the limit as x approaches a of f of x. Now that we have these limit laws, let's go ahead and put them to use by investigating a few examples. So the first example, we are asked specifically, use the limit laws to evaluate the given limit. So that is, we want to go kind of through these step by step and see what the limit laws tell us. The first thing that we're going to notice is that we have a limit of a function plus a function plus a function. So we can break this up into 3 separate limits, which is really our first limit law. That is, this becomes the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 4x plus the limit as x approaches 2 of 5. And then we can start using the individual limit laws to break this up a bit further. And we'll just kind of go one at a time, work our way from left to right, and we'll be nice and methodical and patient with the process. So the limit as x approaches 2 of x squared, if you look at your note handout, that's precisely limit law number 9. Now, you never have to tell me what limit law you are using, but just for this first example, I'm going to go ahead and indicate those limit laws so there's no confusion. But you never have to do that. So by that 9th limit law, this is really just 2 squared. It tells us essentially we can take this 2 and substitute it in for x. And then in the next piece, we're going to have to end up going back to the limit law that tells us we can pull a constant out. So that is to say this constant 4 can be pulled out front. And this is limit law 3. So this would be 4 times the limit as x approaches 2 of x. And we saw in our limit law number 7 that the limit of a constant is always that constant. So the limit as x approaches 2 of 5 is simply 5. So finally we have 2 squared is 4. The limit as x approaches 2 of x, if we look at the 8th limit law, is 2. And remember, you don't have to tell me what limit law you are using. I'm doing that simply to make the connection in this first example. And we end up with the value of this limit is 17. And one thing I do want to really emphasize here is, once again, the use of proper mathematical notation. So an equal sign at each step, organizing whenever possible in this single vertical column. And as we break up that limit, we rewrite the limit at each step so we can kind of clearly see what's happening as we proceed through the problem. One of the most kind of commonplace where points will get deducted for Calculus 1 students in the first few homework assignments is for kind of abuse or misuse of notation. So that is something to pay particular attention to as you're working through your homework, because you will lose points for not using mathematical or correct mathematical notation. Okay, so in our next example, same idea. We want to use our limit laws to evaluate this limit. And note, because it's a limit of a quotient, as long as we don't end up dividing by 0, we can take the limit of the top, divide it by the limit of the bottom. So we just make that mental note. So we have the limit as x approaches 2 of x squared plus 4x plus 5 in the top, divided by the limit as x approaches 2 of x plus 7 in the bottom. And hopefully when you look at that limit in the top, you realize we don't have to think too hard about this, because it is precisely what we did in the previous example. So we're not going to recreate the wheel. We're just going to use that work we've already done. So 17, and in the bottom we'll break that limit up using our first limit law into the limit of the first plus the limit of the second. And then furthermore, we've seen that the limit as x approaches a of x is just a, and our a value is 2. The limit of a constant is that constant. So the value of this second limit is 17 ninths. And to kind of wrap up this example, I would like to make an observation. If we go back to our starting point, this first limit, we're taking the limit of the function x squared plus 4x plus 5. So note, f of x is a function x squared plus 4x plus 5. And just for fun, note, if I was to evaluate this function at 2, you would get 4 plus 8 plus 5, which is 17. So in this case, what we've hopefully connected is the limit as x approaches 2 of the function is equal to f of 2. That is to say, this 2, in a sense, was just substituted in for x. And that's not a coincidence, but at the same time, it's not something we can always do. We need to be in a special scenario. Okay, well, let's look at the next example. Similarly, we're taking the limit of this rational function. Let's call it g. So we have g of x is x squared plus 4x plus 5 over x plus 7. And g of 2, note if we were to evaluate the function at 2, we get 17/9. And lo and behold, once again, the limit as x approaches 2 of g of x ends up being g of 2. And again, I'll note it's not a coincidence, but it's not something that we can do in general. It turns out that what we are using is something called the substitution property. And the substitution property tells us that if the function is a polynomial, so think f of x above, or if the function is a rational function, so think g of x above, a polynomial divided by a polynomial. So if you have a polynomial or a rational function and a is in the domain of function, that is if it makes sense to substitute in a and it's a polynomial or rational function, that is precisely what you do. And you get back f of a. Now, the substitution property, when we can apply it, at least in the beginning, it almost seems too good to be true. And we are very happy when we get to the point that we can apply the substitution property. But a common mistake is to apply it when we are unable to do so. So whenever you apply that substitution property, and we'll practice it here in upcoming videos, we're always going to justify it by putting a little SP over that equal sign. So that SP indicates to me that you are using and you've thought about the substitution property. And once again, you can do this as long as you have a polynomial or a rational function, and this a, where you're taking the limit, is in the domain. Now, it turns out the interesting examples, the ones that will require a bit more thought and work on our part, are when we cannot immediately apply the substitution property and we instead need to do some amount of algebraic manipulation. And that's where we'll pick up in our next video. So stay tuned and take care.